we are continuing our exploration of organic macromolecules, the molecules of life. Specifically today, we will investigate lipids. This content is covered in the Campbell Biology in Focus textbook, Concept 3.4, found on pages 53 to 55. Lipids are fats, oils, waxes, and steroids. And the one thing that all lipids have in common is their insolubility in water. And that means lipids do not mix well with water, and lipids cannot be dissolved in water. We know that water is a fantastic solvent, but water cannot dissolve lipids. Fats and oils are very good sources of food energy. In fact, in a single molecule of fat, there is considerably more energy stored than in a comparable amount of carbohydrate. There's more energy per gram in fat than there is per gram in carbohydrates. And we know carbohydrates are excellent sources of food energy, but lipids actually store energy even more efficiently than carbohydrates. Foods that are rich sources of lipid include things like bacon. The white part of a strip of bacon is lipid. The red part of the bacon is protein, but the white is lipid. So something like a steak, for example, is a rich source of protein, but it also contains fat, which is a lipid. Nuts contain natural plant oils, which are lipids. All fried foods, of course, will contain high lipid content. Now, just like carbohydrates were subdivided into smaller categories, remember with carbohydrates we had monosaccharides, disaccharides, and polysaccharides. Well, in a similar fashion, lipids, the major category, lipid, can be broken down into smaller subcategories. And the first of those is triglyceride. So we're going to talk about triglycerides, what they are, where they're found, and how they function inside living organisms. So the image down at the bottom here, it says it's a fat molecule. This entire molecule is one molecule of triglyceride. And yes, it is a fat molecule. That's another name for it. The components of a triglyceride, in this gray box, you see this 3-carbon alcohol. This is called glycerol. And then there are 1, 2, 3 hydrocarbon chains. These are very long chains of carbon and hydrogen, carbon after carbon after carbon after carbon. These long hydrocarbon chains are called fatty acids. Palmitic acid is just one example. These are fatty acids. So each molecule of triglyceride has 1 glycerol, that's the gray box, and 3 fatty acids, which are joined to that glycerol by dehydration synthesis. And we've talked about dehydration synthesis before. It's simply the removal of water to join 2 components together. Now, let's take a closer look here. If you look in the fatty acid chains on the triglyceride, the energy that is stored in a fat molecule is actually stored in these chemical bonds, these covalent bonds between the carbons and also between the carbons and the hydrogens. Every little stick that you see in this picture, that's a covalent bond, and that's energy that is stored. And sometimes on a fatty acid, if you look at these bonds in between the carbons, you'll notice that they are all single bonds. And I'll explain more about that later, but that just means that the fatty acid is going to be nice and straight. It also affects the way this molecule behaves. whether it is saturated or unsaturated. So we're going to take a closer look at what those terms mean. Let me go to the next slide. This shows it really well. So if you look, just ignore the pictures at the bottom for a moment. If you look at this, what I'm pointing to up at the top here, this is one fatty acid. So this is not an entire triglyceride. We're only looking at one single fatty acid. And notice it says that it is saturated. You've heard of saturated fat, which is made up of saturated fatty acids. Well, it's saturated because all of the bonds in between the carbon atoms are single bonds, and that means each carbon atom is bonded to 2 hydrogen atoms, except for the final carbon, which is actually bonded to 3 hydrogens. It's fully saturated with hydrogen. You could not possibly add any more hydrogen. There's nowhere to stick any more hydrogens on there. But if I look at this fatty acid, it is not fully saturated or fully loaded, you might say, with hydrogen. Notice that this carbon atom and this carbon atom seem to be missing a hydrogen here, and we seem to be missing a hydrogen here. We're no longer fully saturated with hydrogen. And the reason is simple. It's because there's a double bond between these 2 carbons. And we talked about this in a previous lesson. Each carbon atom can only form, do you remember how many bonds? Each carbon atom can form 1, 2, 3, 4 covalent bonds. So if this is a double bond right here, that's 2 bonds, 3, 4. That means this carbon atom cannot form any more bonds. You cannot stick another hydrogen in this spot. Likewise, this carbon already has 1, 2, 3, 4 bonds, so you're going to have to leave off a hydrogen in this spot. It's unsaturated. Now, why does that matter? Why does this make a difference? Well, a couple things that you can just see visually. If the fatty acid is saturated, it's very straight. It runs in a straight line. Look at how all these carbons are lined up in a straight line. If it's unsaturated, there's going to be a bending right where that double bond is. You notice there's a kink in that fatty acid. It also means that where the double bond is a little bit easier for animals to digest and break down. So unsaturated fatty acids tend to not linger in the body as long. We can digest them more quickly, whereas saturated fats tend to linger in our circulatory systems. That's why saturated fat is sometimes linked to heart disease, because it can linger and clog arteries and so forth. Another difference between the two is unsaturated fatty acids do not pack together as tightly, and so they tend to be more fluid and more liquidy. So if we look at an unsaturated fat, it doesn't even really look like a fat at all. It's a liquid. We call it an oil. So corn oil, soybean oil, peanut oil, all those cooking oils that you buy at the grocery store, they are liquid at room temperature because they are unsaturated. They have double bonds in between the carbons. But if we look at animal fat, or the milk fat that's in this butter, that's made up of purely saturated fatty acids. So it packs more densely together and it becomes a solid at room temperature. Chemically, whether it's a fat or an oil, it kind of looks the same. I mean, this molecule called a triglyceride could be a fat or an oil. It really just depends on whether or not we have any double bonds in between these carbons. Now, in this particular picture, I don't see any double bonds in between carbons. So this tells me this would be a saturated fat. This would be an actual, probably an animal fat that was made by an animal's body. Now, when we think about fat, we automatically are conditioned to think negative thoughts. Too much fat in the diet can clog our arteries. cause heart disease. I've already mentioned that. Too much of a good thing can be a bad thing. But it's important to note that saturated triglycerides, that is animal fat, does play some important roles and has some important positive functions in the bodies of animals. And I've tried to illustrate a few of those. Underneath your skin, underneath the epidermis and the dermis, you have a layer of subcutaneous fat. All humans have this. It's a thicker or thinner, depending on the person, depending on genetics and other factors. But we all have it, and all animals have subcutaneous fat. And if you're a seal or a sea lion, you have a very thick layer of this subcutaneous fat because you need to hold in heat. These animals live in typically very cold ocean waters, and they need that thick layer of fat to protect them and provide thermal insulation. If you are a bear preparing to hibernate, you need a thick layer of subcutaneous fat for long-term energy storage. When bears are hibernating, they don't eat, they don't go out and find food, so they're having to live off of the energy stored in their subcutaneous fat. And that is quite a fat bear right there in that picture. Apparently, he is ready to begin hibernation. The most bizarre picture here, and I'm sorry if this is grossing anybody out, but we're looking at a photograph of surgery that is being performed on what looks like a cat. We're looking inside the abdominal cavity of the cat on one side of the spine, and you see a little bit of a pink organ here. That's one of the kidneys of this cat. And notice you can hardly see the kidney because it is completely encapsulated in a thick layer of white fat. And you think, boy, that must be a very morbidly obese cat. That must be a terribly unhealthy animal. But no, your kidney is encased in fat, much like this. The purpose of it is to provide cushioning and protection of that very delicate kidney. There's lots of very tiny blood vessels inside the kidney, and they have to be cushioned and protected from damage if we have a fall or any kind of trauma. Another really important function of fat is fat forms a coating on the surface of our nerve cells. You're looking at a neuron or a cell in your nervous system. This could be a brain cell or a spinal cord cell. And this long strand of this nerve cell, which is called the axon, is covered in a fatty coating called myelin sheath. It's a protective coating that helps ensure that the nerve message travels efficiently down the axon. Without that myelin sheath, your nerves start to short circuit and you have problems with your nervous system. I'll give you a specific example of that. If you know anyone who's been diagnosed with MS, multiple sclerosis, the main symptom of multiple sclerosis is the myelin sheath deteriorates on motor nerves, the nerves that carry messages from the brain out to the muscles of the body. Those nerves lose their myelin sheath, and so the nerve signals start to short circuit, and the brain has a difficult time communicating with the muscles. It makes walking and movements more difficult as the disease progresses. Let's just kind of sum up what we've said about saturated triglycerides. Each molecule of triglyceride is one glycerol bonded to 3 fatty acids. And if those fatty acids have nothing but single bonds in between the carbons, it will truly be saturated. It'll be a solid at room temperature. And we tend to refer to those as true fats. Now, positive functions of saturated triglycerides: long-term energy storage in animals, Think about the big fat bear preparing to hibernate. Insulation to protect from cold. Think about the subcutaneous fat, which was keeping the sea lion warm. Protection of body organs. You saw that disgusting layer of fat surrounding the kidney of the cat. And also fat forms the myelin sheath, the protective coating that insulates our neurons, almost like the rubber coating on an electrical wire. If you strip off that coating, the wire is going to short circuit and it won't work properly. Now remember, the only difference between saturated and unsaturated is unsaturated triglycerides have one or more double bonds in between carbon atoms on the fatty acid chain. If there are many, many, many double bonds, we call it polyunsaturated. If there's only one double bond, we call it monounsaturated. But anytime you hear the term unsaturated, that means it's going to be a liquid at room temperature because of the double bonds and because of that bending of the fatty acids. They don't pack very tightly together, and so they remain fluid and liquidy. And sometimes we call them unsaturated fats, but really they're not fats, they're oils. They're liquids at room temperature, and so probably a better term would be to just refer to them as oils. The function of unsaturated triglycerides is long-term energy storage, especially in the seeds of plants. Now, I don't want to mislead you. It is possible for animals to make unsaturated triglycerides. Fish, for example, store some of their long-term energy as oil. But generally speaking, animals make fats, plants make oils. Fish would be an exception to that rule. Again, fats are solid at room temperature, and they are made up of saturated fatty acids. Oils are liquids at room temperature, and they're made up of unsaturated fatty acid. Okay, so let's talk about the next major category of lipid, which is called the phospholipid. Now, if you look right here where my pointer is moving around, you see the CH2, CH2. That little 3-carbon strip, that's a glycerol molecule. And coming out of the bottom of this is a fatty acid chain. Here's a second fatty acid coming down. If there was a third fatty acid right here in this spot, it would be a triglyceride. It would be a fat or an oil. But if you take away that third fatty acid and you bond onto this carbon, this part here, this part that's in yellow is called a phosphate group. It's a phosphorus atom bonded to 4 separate oxygen atoms. Now this whole molecule is called a phospholipid. It's still a lipid because it has fatty acids, but it's got this weird phosphate group. And I say it's weird because you see this oxygen atom right here has an electrical charge on it. Can you tell what that is? You see there's a little negative sign right here. And actually, I believe right on this nitrogen, there's a little positive sign. This phosphate group has some electrical charge. And that's important. That means water is going to be attracted to it. It means this part, this whole top part of the molecule is hydrophilic. It's attracted to water. And that's very unusual for a lipid because lipids are hydrophobic. They don't mix with water. So here you have a molecule, the top half of it is attracted to water, the bottom half, these fatty acid tails, they kind of look like tails, they're not really tails. These fatty acids are hydrophobic. They try to get as far away from water as they possibly can because they don't mix with water. Now, the easy way to draw a phospholipid is to just draw a circle, which represents the phosphate part. and then two lines coming down off the bottom of the circle, which represent these two fatty acid chains. And here's a pretty cool three-dimensional picture of what a fatty acid looks like. Now, here's why, what a phospholipid looks like. Okay, getting tongue-tied here. Here's why phospholipids are so important in biology. They are just super important. It's because if you have a large number of phospholipids and you expose them to water, the fatty acid tails, which are hydrophobic, will turn away from that water. But the phosphate part, the phosphate heads, which are the little circles, will turn towards the water. And what that causes is the phospholipids will form into a double layer so that the fatty acids can turn away from the water because they are hydrophobic, and the phosphates can turn towards the water because they are hydrophilic. And that double layer, which is called a phospholipid bilayer, completely wraps around every living cell on Earth. All living cells, animal cells, plant cells, bacteria, fungus cells, all cells are surrounded by a phospholipid bilayer that we refer to as the plasma membrane. It's also sometimes called the cell membrane. Now, this gets a little confusing because if we're talking about a plant cell, like this one on the left over here, it is surrounded by a plasma membrane made out of phospholipids, just like the animal cell is surrounded by a phospholipid bilayer. But plant cells and also fungus cells have an extra layer called the cell wall. The cell wall is not the same thing as the cell membrane. The membrane is made out of phospholipid bilayer. The cell wall of a plant cell is made out of cellulose, which is a polysaccharide, as you know. If this was a fungus cell, it's definitely a plant cell because I can see the chloroplast, but if this was a fungus cell, the wall would be made out of a different polysaccharide, which is called chitin, which we talked about earlier. But the membrane, the plasma membrane, is made out of a phospholipid bilayer. Each phospholipid has a hydrophilic phosphate end and two hydrophobic fatty acids, which we sometimes refer to as tails. The function of a phospholipid, it is the primary component of cell membranes. Now, when I say the word steroid, the image that comes to mind for most people is some muscle-bound Olympian or a professional baseball player that has been injecting himself with some sort of chemical that's making his muscles bulge so that he can hit home runs more easily. Well, that's just one kind of steroid. That's called an anabolic steroid, and it makes muscle growth happen at a faster rate. It's illegal for professional baseball players and Olympians to use. Not all steroids make muscles grow. Okay, steroid is just a class of lipid compounds. All steroids, when you look at their structure, they're made up of 4 fused carbon rings, so they kind of look like a little piece of honeycomb if you use your imagination. And the most important, biologically speaking, the most important of all the steroids is cholesterol, which is what you see in this picture. Cholesterol is used to strengthen the structure of your cell membranes, but cholesterol is also the starting point from which all other steroids are made inside the body. So now that I've introduced steroids as a subcategory of lipids, I want to talk about some examples of biologically important steroids I want you to know these examples and know the functions of each. So estrogen and testosterone are two different steroids that we sometimes refer to as the sex hormones. Um, Estrogen is the primary sex hormone made by females. All female mammals make some form of estrogen. It's made by the ovaries, and it is the hormone that causes what we call secondary sexual characteristics. So all the changes that happen in a woman's body at puberty, breast development, and other changes are stimulated by estrogen. Testosterone is the male sex hormone made by the testes, and testosterone causes all the changes in the male body at puberty, the thickening of the vocal cords, which makes boys' voices get deeper at puberty, stimulates the growth of body hair, muscle development, all those changes that happen at puberty in males. Vitamin D is a steroid. It's kind of an interesting story. Some of the vitamin D that our bodies use, we obtain through our diet, through foods that we eat. And milk has vitamin D that's added to it so that we can have plenty of vitamin D in our diets. But your body actually makes its own vitamin D. Every time you go out into the sun, the ultraviolet radiation from the sunlight causes a chemical change in your skin. It causes the cholesterol molecules in your skin to convert into vitamin D. Vitamin D is important because it allows your bones to absorb calcium so that your bones are thick and strong and not brittle. Bile is a steroid compound, a green liquid that's made by your liver. Large quantities of bile are stored inside a small sac underneath the liver called the gallbladder. And the purpose of bile is whenever you eat fatty foods, whenever you consume food that has a large amount of fat, the gallbladder squeezes some of that bile through a small passageway called the bile duct into the small intestine. So as the chewed up, partially digested fat passes through your intestines, I know this sounds lovely, some of that green bile mixes with the fat and breaks it up into very tiny droplets, which are more easily digested. So if you know anyone who's had their gallbladder removed, surgically removed, maybe they had gallstones or some sort of blockage and they had to have their gallbladder removed, you can live a full normal life without a gallbladder, but your body is not going to be able to store large amounts of bile. And so it is going to be more difficult for you to digest fatty foods. People who have lost their gallbladder, when they eat fatty foods, they sometimes get an upset stomach because they're not able to process all of that fat as it passes through the intestines. The last steroid that I've included in my list is cortisone, sometimes called hydrocortisone. A lot of people are familiar with this one because it's used as medicine, topical medicines or injections. Sometimes doctors will inject this compound into a sore joint to reduce swelling. But cortisone is a naturally produced hormone. It's actually made, it's one of the hormones made by your adrenal glands. It is an anti-inflammatory, so it reduces swelling and pain after an injury. Cortisone is also sometimes released by your adrenal glands when you're facing stress. Sometimes it's referred to as the stress hormone. And it will actually increase the amount of glucose in your bloodstream, and it increases the metabolism of glucose in the body. The idea there is you're trying to free up some extra energy that the body can tap into to deal with a stressful situation. That's why sometimes when you're stressed, you have trouble sleeping at night, because your body has produced cortisone and you have this excess glucose floating around in your bloodstream, and you're so hyped up with this extra energy that it's hard to sleep. So cortisone can be good, but it also has some negative consequences. The last category of lipids that I'd like to discuss is wax. And most of us are familiar with beeswax. You can see this white material that has been used by the bees to seal up their honeycombs, to protect the larvae that might be developing in there, and also to protect the honey that they have stored away. Another example of naturally occurring wax in nature is this shiny coating called the leaf cuticle, which is on the top surface of many leaves. It's called the leaf cuticle. It's a protective coating of wax that helps the leaf hold in moisture. So wax generally is a protective waterproof coating that living organisms can synthesize to protect various areas, various surfaces. The two examples being beeswax as an animal example, and then the leaf cuticle is a really good plant example of wax. So I hope you have learned something from this lesson about lipids. We still have proteins and nucleic acids left to cover. Thank you for your attention, and I hope you have a fantastic rest of your day.